Hi, everyone. Thank you. All right, so we're going to kick things off. I'm going to introduce a little bit of the problem and then talk about Mojo and Max today. So I just want to start out with a little bit of a warning here. So many things in AI are hard to understand because so much is changing, so many claims are being made. And so today we're going to be talking about things that only exist today, that only work today, that you can download, you can use. This is not a vision talk. This is real. And so if you'd like, please go download our stuff and use it today. Okay, so what we're doing at Modular is we're building a GenAI native AI software stack. So AI is not a new thing. Much of the world's AI software has been around for 10 years plus, TensorFlow, PyTorch, all these things. We think that AI is so important that we want to actually reinvest in the software stack, do hard work at the compilers and the systems and the software and the algorithms layers to really enable and unlock a new generation of portable AI compute. So what do we see when we look at the world out there? Well, there's a lot of really great software out there. ROCm is amazing, it's open source, but it runs on one vendor's hardware. There's other things like OpenCL, thing I worked on years ago that tried to unify compute, but it gave up all the performance and it's not very usable and things like this. There's also other cool things like Triton that lots of people use and love. It's really amazing at making it more usable and it gives you portability, but it also gives up performance as part of the trade-off. Now this is, I think, AI software as we know it today, lots of trade-offs, lots of different things. They're all built by different groups and different people. What we're trying to do is we're trying to build something that unifies this world. And so we're trying to build something that pulls together the best of usability, because we want developers everywhere to be able to program GPUs, performance, because of course, TCO, cost, speed, latency, all these things matter so much for AI, and of course portability, because we want to see innovation everywhere and we want lots of people to be able to participate. And we think that AMD, for example, has amazing GPUs with amazing flops, and we want people to be able to use them no matter what color their hardware is. So if you zoom out and you look at our stack, I'm not going to deep dive into all the different things. What we've done is we've taken a very first principles approach to this, and where there's a lot of different AI software stacks that are built out of these layered technologies that have been accumulated in AI for many years. What we've done is we built a novel stack from the ground up. And so this means that the matrix multiplications are written in Mojo, which we'll talk about today, all the way up to the higher level stack and models and applications and serving and cluster management and all this kind of stuff. And it's designed vertically integrated to just work. Now, of course, our company's named Modular, and so yes, we integrate with PyTorch, yes, we integrate with all the existing systems. You can take things a la carte, and that's fantastic. But what we really want to see is we want to see a new world where things in AI work, they work the first time, they don't require crazy amounts of configuration, and only by going all the way back to the basics and rebuilding the software stack from first principles can you solve some of these complexity and other problems that the world is struggling with. So, Mojo. It's a new programming language. And so you might ask, why build a new programming language? Isn't that crazy? Well, the challenge out there is that you kind of have to do crazy things to be able to move the world forward. And so C++ is one of the most widely used languages, first of all, in the world, but also in GPUs. If you've used C++, then you've used templates. And if you use templates, you want to stab your eyes out, right? And so the compile time, the usability, this ecosystem, I love C++, but I also hate C++. It's time to move the world forward. Now, lots of folks are trying to make Python domain-specific language thingies. There's lots of examples of this. They're great, and they can be great, but the problem is that they don't work with debuggers, they don't work with profilers, they're not real languages. And so they look good on a slide, but they don't actually work well, and they don't feel good to a developer. And so if you're willing to do the work of building an entirely new programming language, which, by the way, is crazy, you get these benefits of having something that gives you performance, usability, and portability all in one. So what is Mojo? Well, just at a glance, I'll introduce it. It's a Pythonic language, and so the syntax looks like Python. If you have muscle memory, if you have AI coding tools, a lot of stuff just translates over, and it's super familiar, and I think a lot of people love Python, and so why mess with that? Of course, Python's not great for performance, it's not great for GPUs, it's not great for lots of other things, and so what we've done is we built this new language that takes the best of Python, but it's a systems programming language. GPUs are about performance. We want to unlock the full power of the hardware. You have to talk to tensor cores. You need this crazy advanced hardware in order to be able to get AI. And so what we're doing is we're building this new ecosystem around this new language and then building the layers on top of it. Now, Mojo's predominantly open source. You can go download it. It runs on Linux, Mac, Windows, all this kind of stuff. By the way, we have hundreds of thousands of lines of GPU kernels. Please check it out on our GitHub. We also have an amazing community. And throughout this talk, I'll include links, and so you can see examples of what some of the random amazing people in our community are doing. And so please check it out, not just from our site, but on other people's websites as well. Now, I talked about this a little bit before. Why build a new language? Well, it's all about tools. It's about developer experience. It's about productivity. It's about being able to move fast, which is something that everybody in AI really needs, and that's what we're all struggling to do. And so, yes, we get integrated debugger experiences. We get profilers. We get amazing LSP integration with your editor and things like this, because as a language, these tools know about the language. And that's something that's very different from something that looks like Python, but it's actually just kind of embedded into it. Now, I mentioned performance. Well, what do I mean by that? Well, Mojo is actually quite fast. So when you talk Python, people start thinking about, okay, well, is it faster than Python? And the answer is, unless you're doing something really wrong, obviously it's faster than Python. we measure instead from what is the speed of light of the hardware. We want to be faster than ROCm. We want to be faster than CUDA. We want to be faster than C and C++. And so we do this by innovating not just in syntax, but in the compiler, in the architecture of the system, how all these things plug together. And so, of course, we bring best-in-class techniques like SIMD on a CPU, NUMA support, and things like this. But we make it accessible to programmers because while people want power, often they don't want all the complexity and fragmentation, all the details thrust in their face for when they don't want to deal with it. Now, we're here to talk about GPUs, right? This is an AI event, of course, and AI is all about GPUs. And so you can use Mojo to program GPUs from multiple vendors, including AMD. Very excited about that. We bring the familiar GPU programming model to bear. And so if you're used to thread indexes and things like this, you'll feel perfectly at home. And if you're used to writing ROCm kernels or CUDA kernels, then what you'll initially feel is Mojo is just, it feels like C++, but it's in a Python syntax. Well, this is fantastic because it's really easy to learn. You can bring all the idioms that you know, and you can bring it over. And again, you don't get C++ template error messages, but you get the power of generic programming and things like this. Mojo is also not limited. So it's not just tile-based programming, though yes, we do that. It's also about general purpose AI applications. It's about other things you want to do with the GPU. Yes, you can write a ray tracer in Mojo. You get the full power of your hardware. Now, when I talk about the full power of the silicon, GPUs are complicated. Let's not ignore that. Let's not try to sugarcoat that. And so you have to handle this complexity somehow. Some people say, we will have a magic compiler, and we'll put it in the compiler and it'll be a black box and just trust us it's going to be great. Well, it's great until you have to look at compiler IR dumps to debug what went wrong, right? This is the unspoken truth of many of these systems. Mojo's approach is completely different. We don't bury magic into the compiler. What we do instead is we enable programmers to have access to the full power of the GPU. So yeah, you can use inline instructions for AMD. You can go all the way down to the silicon and have full control over the system. But then you, as a programmer, get to build abstractions, libraries, that now you can see the source code for. And so if something goes wrong, you can debug it. You can step into it, which is a completely different developer experience. Now, I'm not going to spend too much time talking about it, but Mojo is also very unique because it's a programming language designed for very fancy MLIR compiler things. I'm not going to nerd out about compilers today. Well, one of those important things is called a graph compiler. A graph compiler is what takes your AI model, and it takes all the kernels you write, and it turns those kernels into the best thing possible for that model. Because a lot of kernels you want to write should be generic. They should be reusable. They should work with lots of different shapes and different data types and things like this. But when you run it, you want full performance. And so by integrating Mojo, the source code, and the compiler and the stack with the graph compiler, what we get is this beautiful world where we can have single source of truth for our algorithms. You can have one implementation of, for example, matmul that can scale across multiple different hardware, different generations, different D-types, and all of these kinds of things. But you get specialized implementations, which makes managing and scaling AI a completely different ballgame than what we're used to with hundreds of different permutations of kernels and trying to find them all and manage them and all the nightmare that we're used to. Now, one of the other cool things about this is that you can call this stuff directly from Python. And so, yes, we integrate with PyTorch. You can work directly with these kernels in all the ways that you're used to. And so we love Python for what it's good for. But when you want performance, Mojo is your thing. Now, let me tell you the secret weapon. But we're not going to keep it a secret, of course. The thing that makes Mojo possible is called metaprogramming. And so if you're familiar with C++ templates, think about the good parts of that, like the power it gives you, and let's take that power and remove all the pain and suffering. And so I'll talk a little bit about this in the time we have today. But the key thing to know about metaprogramming in Mojo is that it is just programming. And so if you think about something like C++, you have for loops and code, but then you have templates. And so you have two different worlds that are trying to live together so you can write a generic program and then actually the program. And so Mojo removes that difference. It's the same code that you use for compile time and at runtime. And again, this gives you power as a programmer to invent new kinds of abstractions and effectively extend the compiler, air quotes, by writing libraries and writing Mojo code. Well, let's talk about some of the ways how that works. Well, so in Mojo, functions have basically two different kinds of things that they can take. You have arguments. Arguments are normal things. They're the dynamic values that get passed into your program. And then you have what we call parameters. These are things known at compile time. And so values in Mojo can have two different lives. One is provably known at compile time, and one is at runtime, provably dynamic. And now what Mojo allows you to do with a very simple approach is to have plus, function calls, recursion, all these things. Of course they work at runtime, and of course they work at compile time, and you have one thing to manage. Well, this makes everything simpler. This makes it so you can define really advanced compile time features, for example, working with crazy advanced layouts that you need for tensor cores, without having all this complexity and without the terrible error messages that we're used to from C++. Now, Mojo has a very powerful generic system, and so if you're familiar with languages like Rust and things like this, Mojo has traits, and this makes it very easy to be able to generate very good error messages when you do things that are wrong, because you're not having to instantiate all the templates to figure out what went wrong. You can actually report the error right at the site that you do something wrong. And so this gives you very powerful new ways to model programs. And so this is why people love writing Mojo. So what you're doing is you're taking all the good things you love about Python, you're building in metaprogramming, and then you're giving very expressive powers to library developers to invent new abstractions so that they can solve problems that only they understand and they know the best, not just some compiler person thinks is good. So when you get to playing this forward, now you start talking about, cool, I have functions that can take compile time values. Well, we want to be able to enable metaprogramming that's very generic. And so in Mojo, this is super simple. Again, you don't have templates and weird things with type defs and using declarations and stuff like this. You get one keyword called alias. Alias is like a compile time variable. And so because types are just compile time variables, it serves the purpose of something like a type def. But you can do very powerful things here. And so in this example, we have a Fibonacci function. Right? It looks like a very normal function you define on line 10. You can totally call that at runtime. That works just like you'd expect. It does recursion, awesome. Well, you can also, on line 19, call this at compile time. And what happens is Mojo guarantees that that function is called at compile time, and the answer is put into your binary. And so you have full control over what the compiler is doing and full ability to express lots of fancy algorithms that go way beyond Fibonacci, of course. And this power, this flexibility is what empowers you as a library developer to take advantage of this very fancy system. Now you play this forward, Mojo talks to things like low-level assembly and MLAR and very fancy compiler stuff. And when you combine that with powerful metaprogramming, what it enables you to do is write very generic code that is also portable and write that in a very straightforward way in libraries. And then you can build things like a barrier function and have very simple, very generic algorithms that then have a tremendous amount of power inside of it. And again, the cool thing about this is you get that power, you get that flexibility, you get the configurability, but there's no magic. And so if you want to step into this in a debugger, you can totally do that. It's just that easy. Okay, well, let me tell you about this very fancy thing called Python out there. Python is great. Here's a fire-breathing Python, I guess. I don't know what this is, but we do love Python, right? And we talk a lot about GPUs, but you can use all this stuff within your existing Python ecosystem. Like, we as programmers are very pragmatic. We don't want to have to rewrite everything just to adopt new technology, right? And so one of the most amazing things for Python programmers is that you can directly call from Python into Mojo, and you don't need bindings. What this means is that if you're a Python programmer and you're building and building and building, and you're being very productive and lots of cool things, all the things we love about Python, but then you run into performance problems, well, now instead of having to switch to C++ or Rust or PyBind or like all this super crazy complicated stuff, you can just move a few for loops into Mojo. Now it goes 1,000 times faster, and you can call it directly from your Python code. You don't have to rewrite everything, don't have to change your ecosystem, you can adopt it piecemeal. And if you're super crazy, you want to unlock the real power of all the flops, why stop there? Take the algorithm to the GPU. Well, this is huge. We already have people in our community that are doing this, and these are folks that have never programmed a GPU before, and they always thought the GPUs were scary or they weren't smart enough or things like this. And so by making things easy and accessible and adoptable, what we're seeing already is people are like learning GPU programming for the first time, and I love this. This is the power of technology and community. Now, our whole point here is to empower developers. Hopefully you get that from the entire gist of what I'm talking about. And so one of the cool things about this is that if you're a Python developer, you don't have to like switch from the things we love about Python to curly braces, right? We don't have to switch to these crazy compiled makefile, CMake, whatever it is that we're using again these days, inventing all the same makefile stuff over again. You can experiment with things. And so it's really easy to play with this, and you can work with it in notebooks and all this kind of stuff. And if you care about performance, again, you get this full power of the hardware. And even CPUs are cool. Like they have amazing amount of TOPS within the CPU. They have amazing features. And a lot of modern AI systems are not just the GPU. It's about the GPU and the CPU working together. And so Mojo is really quite unique in that it can scale through your entire software lifecycle, and it can dramatically reduce the complexity at every single level of the stack that you might hit. And it can scale with you as you learn from basic stuff in Python to the crazy advanced, I want to go do a tensor core and build amazing, the flash attention 17 or something that somebody might come up with next. Now, of course, I don't have time to talk about everything. There's a tremendous amount of awesome stuff in Mojo. If you're interested, please do check out our webpage. Go to modular.com and you can look up Mojo. Things like zero-cost abstractions. Yes, it's faster than Rust, even on CPUs. Full dynamic shape support, you can get layout tensor, tile-based programming, like all the cool stuff that you'd expect from a modern system. And so there's a tremendous amount of depth there we just don't have time to talk about today. And so you may be asking, okay, this sounds cool. Again, I told you you can download it today. This is not a hype vaporware talk, but is it ready? Can you use it? The answer is yes, and there's lots of different ways to do that. So going back to our stack, one of the things we hear from enterprises is they want to deploy and scale not just one model or one use case, but they have a fleet of GPUs and they're managing these things. And they have many different product teams. They're all trying to throw workloads onto these GPUs and they have to manage this. And so Mammoth is a technology we're just unveiling now that allows you to scale into this, get amazing TCO benefits, disaggregated prefill, like all these cool things that you'd come to expect from a cluster scale solution, but one that scales with you. Because the thing that we all know is that research is not going to slow down. AI is not done, it's just getting started. And there isn't one right solution. You need something that can scale into the full complexity and the full chaotic madness that is AI today. So the other cool thing about Mammoth and the other cool thing about our entire stack is that we have a single implementation that scales. And it scales not just across research, but it scales across hardware. And we love AMD. Like, we're super excited about the 355 that we all heard about today. We also do love our friends at NVIDIA, and they have great GPUs too. And so one of the cool things about our stack is it's natively heterogeneous. And so if you have a commit that works on NVIDIA, you have some AMD in your fleet, and you want to use the best algorithms that use the memory capacity of the AMD compute. If you have other models that don't need that, well, you can actually have the best solution for your workload instead of having to decide upfront what your workload will have to be 3 years from now, which of course nobody can predict. And so this technology allows you to scale, gives you and your platform engineering teams the ability to negotiate the crazy chaotic waters of AI and actually be able to scale into this and manage it. So we have a lot of stuff going on, and I will only talk about one really exciting thing. Of course, that's AMD 355. We're very excited about this new hardware platform, all the power and the flops. We think that it's just everything that they've got going on, from the memory capacity to the Float 6 performance to just everything that's happening with this chip is just amazingly exciting. And we can't wait to ship this as soon as the hardware is available. So with that, that's the end of my talk, and I'm very happy to answer questions. I'm happy to nerd out about like infinite layers of detail at all levels of the stack.
Hey, Chris, amazing talk. Congratulations on the partnership and the launch with 355. Question, right? Mammoth, it's very exciting. Actually, like we were actually looking for that kind of tool. Is it native with Max and Mojo, or can I deploy with CUDA directly, or
Yeah. So Modular's whole approach is to meet people where they are. And so I talk about our native stack because obviously we're very proud of them. We put a lot of energy into it. But yes, you can put native CUDA kernels into a max model, and you can directly integrate CUDA, like existing CUDA kernels. Of course, they'll only run on NVIDIA hardware, as you'd expect, right? But being able to meet people where they are is really important. This works at every level of the stack. So if you go up to PyTorch, like yes, like we have a very fancy way to have GenAI native models, and that's cool. And we have over 500 of those, by the way. It's very exciting. Great for the best performance and TCO and all the things you might want. But it turns out PyTorch is amazing for research, amazing if you just want to fiddle with one kernel. And so yes, our tech plugs into PyTorch. At the Mammoth level, yes, it works great with Max, but it can also talk to VLLM and other solutions as well. And so we want to make sure that we can enable and integrate in ways that our customers and everybody in the ecosystem wants to work. Yep.
Thanks. It looks really cool. I'm curious, though, as the developer of Swift, why go in the direction of Python just because that was what the community was using, which would have been the same argument that could have been made against creating Swift in the first place? And why not look at other models rather than moving into a better Python?
Great question. So let me reinterpret cast your question here a little bit. So you said back in the day of Objective-C, y'all Swift people, that's me, decided to invent new syntax. And that seemed to work. Well, why? Well, the answer is Objective-C had a syntax problem. Right? It was not very adoptable. It was not very usable. Pointers, square brackets, it was very scary, and it prevented people from adopting them. Right? So you fast forward today, and what is the lesson learned? And by the way, I love Swift. It's not a GPU thing, and like it doesn't scale, and so that's why not Swift literally. You fast forward today, we have exactly the same thing going on. Today, it's not Objective-C that the world is stuck with. That's gatekeeping new developers and gatekeeping and preventing people from learning how to do this new technology. Today, it's C++. So C++, again, is widely used. Lots of people appreciate it. There's so much technology that we have to thank C++ for because it enabled, just like back in the day, Objective-C enabled the first iPhone. But the sad reality is that C++ is difficult to love. This is my opinion, maybe you disagree. And so we need something better, right? And so we decided, you know what? Actually, Python's pretty great. Turns out, different people can have different opinions, but Python doesn't have a syntax problem. It has an implementation problem. And so what we did is we took the best part of Python forward, and we said, AI is fundamentally Python. Don't fight it. It's actually beautiful. Again, different people can disagree. This is my opinion. And so take the power and the beauty of Python and then enable and open the developer ecosystem, because, I don't know, my kid knows Python, does not know C++, does not know Rust or Julia or many of the other things you might be thinking of. Let's bring that technology and that new platform to the developers that are in Python, because I think it's pretty amazing. So I don't know if that answers the question, but that's how I think about it.
Hi, Chris. Thanks for the talk. Just wondering, like with Mojo coming in, trying to bridge the gap of performance and usability, and we can leverage it all. What do you think where the bottlenecks lie in the future as we are trying to evolve, we are trying to build compilers? Are the bottlenecks in the language or in compilers or in actual developers' mental model itself?
Yeah, that's a great question. So we are not working on this today, but it has been pointed out to me that Mojo is actually perfect for solving things like FPGA programming and HLS and things like this, because a lot of the DNA that we've built into the language. And so what I would love to see is Modular is very focused on AI, right? As a consequence of that, we are using Mojo ourselves. We have hundreds of thousands of lines that we have built. We have more Mojo in our code than C++ these days. It's amazing. As a guy who has written too much C++, this is amazing. But as we play forward, and as a consequence of building out AI and AI solutions using Mojo, what we're focused on is we're focused on things like tile-based programming. And so we have a very fancy layout abstraction so that you can program tensor cores and you get generic code against tiles and things like this. But as I think forward and as I dream, again, we're not working on this, there's domain experts in many different fields. And so when I look at, for example, FPGAs, right, there are amazingly, incredibly parallel architecture, right? There are domain experts that have built algorithms that are great against these new forms of compute. And so what Mojo can do is that it can empower those developers to go build and innovate and then bring forward a software ecosystem that can scale. And so I don't know what the next limitation will be. I'm just right now very excited about where we are and what we're able to solve. And so I don't know kind of what the fundamental headroom will be. I haven't thought about quantum or DNA computing or analog or maybe, I mean, there's lots of, computing's a big world out there. But I think it's pretty exciting where we are today.
Okay. I'm basically what you'll call a old style FPGA type of person. So I'm not really a software person, but this is just my observation. But I think this conference it seems like Xilinx, the former Xilinx people are kind of missing from this conference. That's just my impression. It seems like the Radeon people conference. So my concern I have is I think the FPGA toolset like Vivado, or before that it was called ISE with Xilinx, is probably too IC design focused. And even the term FPGA programming to FPGA hardware background person like myself I won't say it's offensive, but it's a misnomer because FPGA really is a hardware device now it's being kind of explored by software people.
Okay,
and there's a cultural issue.
If you don't mind, I'm not an expert on FPGA programming, and I'd love to bubble it back to AI because that's the topic we have here. So.
Thank you, Chris. Just a follow-up question to the lady over there, right? She was asking, what about other accelerators and like non-GPUs?
Yeah.
How do you see the support? Like the way, right? The other day I was listening to the talk from the Triton team, the Meta team, right? The fundamental challenge, the way they were explaining was, hey, to program for other non-GPUs, you need to understand the microarchitecture.
That's right.
And would love to hear your thoughts on that.
Yeah. So I mean, the Mojo and the Max tech stack is uniquely designed for that. We don't have anything to announce today, but ASICs are definitely on our list of concern, and it was designed from first principles to support that. In my history, I worked and scaled Google TPUs, which is an example of a very large-scale, deployed-at-scale accelerator. And I don't know all of the world's chips, but I know that we can scale into that class of architecture and many others. And so we don't have anything to announce today, but I'm very excited about that, and I'm very excited about pulling this back together. Into +1U, you can't have, like, in air quotes, magic abstraction like Triton, for example, tries to provide, because there are fundamental differences in hardware. And so if you need fancy pointer indexing that's different than what that fancy compiler stack promises to provide, well, suddenly you're sitting there fighting the technology, you're fighting the compiler, fighting the system, and there's great claims. What I care about is actually proving things. And so I do not have anything to say. Everybody should be skeptical of any claims until they can see it. And so Max and Mojo don't run on FPGAs, doesn't run on ASICs. Let's focus on what it does today, which is it's an amazing thing for CPUs and GPUs, and perhaps someday later we'll have more to talk about. Is that it? Awesome. Well, thank you, everyone.